And he has sort of he has a long and distinguished career of research and service in mathematics. He's been an editor of several prestigious journals, including Potential Analysis, ALIA, Annals of Probability. He's written a number of what I consider to be seminal papers on planar Brownian motion. That's sort of where I'm most familiar with his research, but he's done a lot of work on other areas as well, focusing primarily on the interplay between probability and analysis. And he has very generously agreed to speak to us in what is dinner time in Indiana. And so we're very happy to have him here. And I guess that's it. So please, Rodrigo, whenever you're ready, go ahead.
Thank you. Thank you very much, Greg, and good morning to everyone. It's a pleasure to be here. You know, I looked through your seminar. It's a very impressive list of speakers. You're really running a wonderful seminar. I like Chris Bursey's statement that some of the theorems here, well, what did he say? Some of the statements are not provable, and some others may be wrong or something along those lines. I like that line in Bursey's talk. Bursey is a good friend and a collaborator, and I don't think he would mind if I stole that line. But in any case, I'm going to try to give you a bit of an overview here, not so much, you know, hit you with all the technicalities, which are plenty here, but rather give you a bit of an idea of what is going on with some of these problems. And I want to start with a little bit of history because I think it's quite interesting. And now I have, all right, there we go. So, you know, a question that excited the interest of many analysts during the early 20th century, was the following basic question: how does the size of a periodic function control the size of its conjugate? So we can just take a polynomial here because, you know, once we do polynomials, you can do any series as long as the constants do not depend on the capital N there. So you look at f of theta polynomial, and then you look at the conjugate polynomial, which is obtained just by permuting the sine and the cosine and putting a minus sign. And then the size, the measure of the size is the LP norm. So the question was really, is there a universal constant Cp depending only on P such that the conjugate function is bounded by the function itself? Now, of course, if you conjugate gives you back the function. So the question is, if one function is an LP, is the other one also an LP, and do they have comparable LP norms? And of course, the question already very, very early on was that if P is equal to 1 or P is equal to infinity, the answer is not, is no. And the problem of interest was to show for a long time that P between 1 and infinity works, okay, for this problem. So of course, orthogonality gives you that polynomials gives you that you have the L2 norms are the same, and this was already known, you know, very, very early on, as soon as Planchel's theorem came up, orthogonality came up. So for general P, the problem was solved by Marcel Ries in 1923, and here is what Ries proved. In fact, Ries proved that if you take the conjugate function of any periodic function, which is really equivalent to what I said before in terms of polynomials, you look at this integral. This is really a singular integral because you're taking the cosine divided by the sine, and so it is not defined when theta is equal to phi, and you have to then take the principal value. Okay. And of course, this is also the boundary values. If you start out with the function f, all right, in the unit disk, in the unit circle, and you extend the harmonic inside the disk, and then you look at the conjugate function of the harmonic function that you obtain from f, and then take the boundary values back to the disk, to the circle, then you get this function f theta. Now, Marcel Ries's theorem was proved in 1923. And it was published in 1927. I always like to point that out because, you know, we get very impatient these days when our papers linger out there for a while. Well, this one lingered for a long time. And in any case, what he proved is that, in fact, what was expected is actually true. And he did it actually for the theorem. He proved the theorem in the circle, but it's equivalent, of course, to proving for the non-periodic case the Hilbert transform, which is the basic Calderón-Zygmund singular integral. And so both of these statements are equivalent. If you prove one, you prove the other one. And again, the conjugate function, the Hilbert transform, is obtained by taking the function f, extending it harmonic to the upper half space, taking the conjugate function, and then coming back down to the real line. And that gives you, in fact, h of f. So now, the discrete Hilbert transform was actually introduced in fact, the Hilbert transform got this name from the discrete Hilbert transform, which was introduced in 1900s or around there, early 1900s. And it's just exactly the same as the Hilbert transform, except you take a sequence, right? A sequence. You take a function on the integers, and then you take the convolution and discrete convolution with 1 over m, right? And of course, this time the principal value here you cannot this is discrete, so you have to exclude 0. And in his paper, Rees proved that the boundedness of the continuous Hilbert transform implies the boundedness of the discrete Hilbert transform also in little LP. Okay, and so here's the inequality. But in fact, he proved more. He proved that in fact the discrete, the P norm, the operator norm of the discrete operator is less than a constant time, which is independent of P, in fact, times a norm of the continuous operator. And then the other inequality was actually sharper. So the discrete is larger than the continuous one with constant 1. And he left these as a question. And then the following year, okay, 1924, and you can see that Tishmarsh actually published his paper in 1926, so a year before Rees's paper. And he proved again, that he turned it around and proved first that the discrete Hilbert transform is bounded. And then from there, he proved, quote unquote, that in fact, you could take this constant C equal to 1, and so that the norms are the same, okay? Now, unfortunately, Tishmarsh was wrong in this proof of this bound. And the following year, in 1926 also, he wrote the following paper. He says, there's an error in my proof, and therefore this should be ignored. The rest of the proof is correct, however. And then he made a little confession here, which is interesting. I should have said that I was already familiar with Rees's method and not merely his result when I wrote my paper. Rees's proof was a very ingenious proof. He proved that for even powers of P, and then by that time there was already interpolation, and so he used interpolation theorem to get all the P's. What Tishmarsh did, he also proved his discrete version for even P's, and then again you do interpolation because you also have the Martingale interpolation theorem. All right, now there is a fascinating history of these exchanges of letters and correspondences between Hardy, Littlewood, Rees, and Tishmarsh, and is written is in an article by Margaret Cartwright, Mary Cartwright, who was Hardy's one of Hardy's last students, I believe, perhaps his last student. And is describe, a lot of the details of, so the bottom line is that there was a bit of a competition, let's put it this way, between these outstanding mathematicians to get this theorem. It's really nice reading. There's a lot of history on these problems. But the problem remained open for many years, despite very good techniques and modern techniques, including looking at Littlewood-Paley theory for discrete Laplacians, which is really very popular subject and very well done, and a lot of other techniques, but one can read some of those results here. But let me go on and tell you a bit more on this problem and how we came about to doing it. So in 1972, Picorides, who was the last student of Anthony Zygmund, who got the Salem Prize for this theorem, he found the best constant, the optimal constant in the Hilbert transform inequality. And this is a funny constant, okay, but the important point here is that it's sharp, of course, and it behaves as P, linear in P as P goes to infinity. And so P star here is the maximum of 1 over P and 1 over Q, the conjugate exponents. And the sharpest is not very difficult. You use powers of these truncation powers in order to make him belong to LP. And the proof actually, Brian Cole, who's a professor at Brown University, had actually proved a version of this theorem a little bit earlier, well, maybe around the same time for the unit disk, but now there are many proofs, and Brian Cole's proof is actually one of them. In any case, you see, because of these, now we have identified the constant. The constant was identified. So then the efforts became to prove that the discrete Hilbert transform is less than the norm of it is less than the cotangent of pi over 2p. Okay, so which is the norm of the operator, right? And so we were able to do this by adopting a technique that has been widely used for singular integrals, which comes essentially from some fundamental work that Richard Gandhi and Nick Varopoulos did in the 1980s, which has been extended in many different directions. Are there any questions that I may address right at this point on anything? No? Okay, so let me go on, the very first thing I would like to do, well, before I do that, actually, I want to also say a couple of words about the famous paper of Calderón-Zygmund. So in that paper, Calderón-Zygmund, of course, introduced the Calderón-Zygmund theory, namely the singular integrals. Okay, so these are convolutions with a kernel, and there are some assumptions on the kernel. It's not that important, but anyway, these kernels, of course, become singular in the diagonal. And of course, now the theory is just enormous, right? I mean, these functions here, the kernels are functions of the convolutions, but the operators don't have to be convolution operators. Now, the discrete version of these singular integrals are just what one would expect naively. Okay, so you take the kernel and you look at it along the integers, and of course, you have to subtract the diagonal. Because you don't have principal value here, you cannot just take limits away from epsilon limits and then let epsilon go to 0. That would make no sense. In any case, but Calderón and Zygmund make the following remark. There's a Tishmart and Rees. These operators have comparable norms. All right. So in fact, Calderón and Zygmund don't really even prove this theorem. Here's the remark that they make, which surprisingly, many of my harmonic analysis colleagues who are familiar with this paper have not gotten to this small remark, but he says for d equals 1, this remark, so they make a remark. They say, these holes, okay? And then they say for d equals 1, this remark is due to Marcel-Rees, and they prove in the case of general D follows in a similar pattern, and they're correct, actually. The proof follows a similar pattern, but it's funny, I have not seen it fully written down, so we have it written down in a paper, which I will mention again, with Daesung Kim, my co-authors for this some of these extensions to hard dimensions. Kim is a postdoc. He was my student here. He's a postdoc at the University of Illinois, a Duke instructor, and Mateusz Kwasnicki is a professor at Wrocław University Technology in Poland. Any case, so if you keep track of constants, you see that this the discrete Hilbert, the discrete singular integrals are bounded by the continuous one and same norm up to this constant. Okay, this constant that depends on dimension and it depends on this kappa, on this bound for the gradient and the operator. And the other way around, this is actually true for all for a large class of operators. One has to do a little bit of restriction here, but I probably should not go so much into that. Okay, so this actually has been of interest to a lot of people. Stein and many of his collaborators actually studied these so-called analogous theorems in harmonic analysis for discrete operators. So they look at maximal functions, they look at singular integrals, they look at Fourier multipliers, and there's some beautiful connections of that theory of those results to analytic number theory, which certainly is not a subject that I know at all myself. But it has been a lot of interest on this subject. And again, I'm not really going to go into it because I really want to tell you a little bit of how the probability comes into these problems. So the Riesz transforms are the extensions of the Hilbert transform in higher dimensions, okay? So they are given, of course, they also obtained by from semigroup theory by taking the derivatives of the inverse of the Laplacian, the square root of the Laplacian, but they're also singular integrals. Now, in fact, Ivanich and Martin, Tadeusz Ivanich and Gavin Martin, in 1986 proved that the constant, the LP norm of the Riesz transform is exactly the same as the LP norm of the Hilbert transform. And this had been actually a question that was raised by Stein and among many other questions early on, and Stein actually had proved this, that the norm of the Hilbert Riesz transform is independent of dimension. So, there was a desired, and for those of you that work sort of in stochastic analysis, you may know Paul-André Mayer's theorems for the Ornstein-Uhlenbeck and Wiener space. Okay, so these are theorems that were of interest because of that. You wanted to extend results to Wiener space. But the result actually, we proved that in they proved it before us. Their paper was published after us. So this is a paper got with Gangwang, and that's where the probability actually came in. So we also verified these results. So the question that is also of interest is are the discrete Riesz transforms which you obtain just exactly the same as the Calderón-Zygmund construction by putting the kernel and doing it along the integers, is it the case then that these operators also have the same norm as the operators of the continuous version, and therefore the same as the discrete as the continuous Hilbert transform and the discrete Hilbert transform? In other words, all of these four operators, independent of the dimension, they have the same norm. And in fact, we conjecture that they do. Again, this inequality follows, right, from what we just talked about. This inequality had a kappa here, but here the kappa just depends on D. So up to this constant that depends on D, right, these operators have the same norm, and our conjecture is in fact that they have the same P norms. But it was quite not trivial to prove the theorem in one dimension. So here we are far from being able to prove this conjecture. Let me just talk a little bit of how these proofs are come about using probabilities, stochastic integrals. So there's this theory that Bergholder developed in the 80s This is based on subordination and orthogonality. So you take a stochastic integral, okay, with the integrand k and a stochastic integral in the integrand h, and you said that n is subordinate to m, right? And you write n less than m if the norm of these, so this could be in d-dimensional space, and the norm of these is less than or equal to the norm of the h of the corresponding h for the m, almost surely for all s's, all right? And orthogonality means that in fact AKS is orthogonal to HS as vectors for almost surely for all s's. Now here are the sharp inequalities. So Burkholder in 1984 proved that if n is subordinate to m, then the inequality, the LP norm of n is less than or equal to P star, this maximum of P and Q, right, minus 1 times the norm of the n. Now, what we proved with Gang Wang and several years later is that if they are orthogonal, then you see you have the constant, exactly the constant that appears in Picorides, that appeared in the discrete Hilbert transform, and there is conjecture for the Riesz transforms. And in fact, these constants are best possible. So our motivation for this problem at that time was, of course, the classical Riesz transforms, but also related to something that is called the Berling-Alfors operator, which has been a conjecture that has been around for a very long time in analysis and various other areas of quasi-conformal mappings. So let me give you a proof of Picorides theorem, all right? You know, there are so many proofs. This proof is really will not be worth a dime at this point. And the reason why I would like to do it is because it tells us how to proceed with the discrete Hilbert transform. So let me take the Poisson kernel in the upper half space, okay, with Paul at W, okay? And you take a nice function. So here, all the functions can be very nice. Everything is already, all the inequalities are already known. So, you know, you just want to get rid of the dependence of, you know, you can approximate with good function, with, you know, functional LP with really functions in C infinity a compact support. So then you take the harmonic extension of the function to the upper half space, right? And you make the following observation. Of course, this is the harmonic extension. So as u goes to the boundary, as y goes to the boundary, the function u sub f becomes f of x, right? As y goes to infinity, the function is very good. And so this actually is order y squared, or y over y squared. So that actually goes to 0. But here's another kind of simple trivial observation, that if you look at y times pi, so you multiply y times pi in here, and then this actually converts into an integral, the integral of the function f, right? So you can convert LP norms of functions in R to just the behavior of these harmonic functions at infinity up to this constant here, right? So now let me take Brownian motion in the upper half space and run it until it leaves the upper half space, right? And we have this cartoon here. You start at 0, y0, and we leave it at the point b tau. So tau is the exit time for the upper half space. And then you look at the harmonic extension is just the expectation of the function, right? Starting at x comma y of f of tau, x of tau, right? Yeah, I use x of tau instead of b tau here. So x of tau is the horizontal part. I mean, the y tau is equal to 0. In any case, and then you see as y goes to infinity, this expectation becomes an integral, just the integral of the function, okay? So it leaves according to the uniform distribution if you start way, way, way up in the upper half space, right? Then you apply Ito's formula, right? And there's Ito formula, and then you let t go to tau, right? And then you have essentially a representation of the function, as an integral, right? As a stochastic integral. Now, how do we get the conjugate function involved here? Here's what we do. So we take this 2 by 2 matrix, which is orthogonal of norm 1, and this is a crucial thing. And then we rotate the gradient of the harmonic function. The Cauchy-Riemann equations tell us that in fact you get the gradient of the conjugate harmonic function, right? So the length of these two vectors is exactly the same because, of course, this matrix this is just a rotation, right? Okay, so you have two martingales here, right? So if you now apply the Ito formula to the conjugate, you get exactly these representation for the conjugate harmonic functions. You see, is just the function, extension of the function, and then this vector rotated by the matrix H, right? And you see, vis-a-vis the conjugate harmonic function is the martingale that comes from the conjugate harmonic function is subordinate to the one for the function itself, and they are orthogonal. So then immediately you have this inequality, right? Apply with the martingales, right? For H and the martingale for F. Now you multiply, right? So you multiply by pi y, and then you take a function nice enough so that these goes to 0, the harmonic extension at infinity goes to 0, and the harmonic extension of u sub f also goes to 0. And what you do, you convert these into Picorides theorem, right? The bound cotangent pi over 2p star. Right? Any questions on this construction? So it's very simple, right? Very simple. And these, of course, was already, has been around for quite a long time. Now, but the beauty of this is that you can do this. You see, we don't have to have the matrix A, that matrix A there. We can take any matrix, right? And of course, now, if we take this quantity, which is called the Martingale transform without the conditioning, right? This is not going to be a function of the exit position. It was a function of the exit position when A was equal to H and we were in 2 dimensions. So if you take a matrix that it has these properties, so this norm, right, just the L2 norm of the matrix norm of for Z and W fixed, right, and then after that you take the sup norm of of the L infinity norm over Z and W, which are elements in RD plus, the upper has space for RD. And then you define this operator, right? Now, as y goes to infinity, it turns out that these operators, so these operators are bounded in LP for every one of the starting point. But as y goes to infinity, these operators are also remain bounded from LP to LP. And in fact, you have these two inequalities. So if you take any matrix A, you get Burkholder's inequality with P star minus 1, right? And if you take an orthogonal matrix A, then this gives you the Picorides type inequality in all dimensions, right? And of course, the question is, what are these operators? Are there these operators, are there interesting examples here? And turns out that yes, in fact, the Riesz transforms are a special kind of these operators with a particular A. I'm going to tell you in a bit what that A is when we go to the discrete case. But you see, you can construct, you can compute the kernel for these operators. So here's a kernel, right? So this is, you take the gradient of the Poisson kernel at x tilde, you take the gradient of the Poisson kernel at x, this pulse, and then you apply A to these, take the dot product with the other one, and multiply by 2W, okay, and this gives you the kernel, right? So here's the remark. Some are these are convolutions, some are not, some are Calderón-Zygmund, some are not, but certainly not all Calderón-Zygmunds will arise this way. However, one gets Riesz transforms at our end, you get Riesz transforms in Lie groups, you get the Ornstein-Uhlenbeck Riesz transforms, right? You know, you take the invariant measure now is going to be Wiener measure, and you're going to take, you know, derivatives a la Malia-Van and so on. And of course, you can just do these inequalities when you want to do them for Wiener space. You can just do them on finite dimension RD with respect to the, you know, to the Ornstein-Uhlenbeck operator, and with respect to Gaussian measure. And then since the constants are not going to depend on dimension, you can just let the dimension go to infinity, and then you get the true Wiener space case. You can replace Brownian motion by other processes, including Levy processes. So there are many operators of this kind that are of interest, and they come from Levy processes. And this actually is work with Krzysztof Bogdan from Wrocław as well. And we have a recent paper on these multiplier theorems via Martingale transforms that appeared just in the Journal of Functional Analysis recently to explore these. But now you see, the question is, and the question that I asked myself a very long time ago is how to construct, how to do this construction to come up with these operators that at the end will give you the discrete Hilbert transform, right? And so here's what you want to do. You want to construct a process in the upper space, which instead of exiting the entire real line, right, it will exit only on the integers. And of course, we know how to do that because we know how to construct, you know, Brownian motion a la Doob, the Doob H processes, right? Those you can force to end at any point you want and compute probabilities of exiting those points and so on, right? So here is what we do. So we repeat the construction, but in the following way. So we take the so-called, so we take the Poisson kernel with pole at the integers, right? Okay, in the upper space. Then we look at this quantity, the summation over all integers. This is typically called the periodic Poisson kernel. Now, in one dimension, by using the so-called Poisson summation formula, one can actually compute this quantity. And here it is, right? So I'm not going to do it, but you can actually compute it, right? So then you see H is positive, of course, is harmonic, right? And so you can condition with this function, and you can construct use of f of x comma y. This is the extension, essentially the extension of the sequence, right? Using these probabilities, right? So these probabilities add to 1, right? So this is a process that start at the point x comma y and exit as x's at n with this probability. It only exits at n. Now, so use of f is H harmonic. So in fact, this function satisfies this equation, the Laplacian plus a drift. And this drift is exactly the Doob H process drift, right? So it has boundary values at n, at the integers, it has boundary values Fn, right? And it is harmonic. So we call it, by abuse of language, the H harmonic extension of f, right? Now the function f, the boundary values of f are not just going to be Fn, right? You know, no function, no nice PDE is going to just, you know, take values at boundary values at a countable number of points, right? So the function actually has boundary values at other places as well, okay? But if you want to look at it in terms of expectations, right, with respect to this Doob H process, which I'm just about to mention, is going to just go to the integers, okay? The value of the function of the integer. So what is the Doob H process? Well, you just take the Brownian motion with this drift, okay? And you see, then you look at the Martin again, you turn the handle and you get stochastic integrals, okay? They got a drift, right? Then you see, using the equation, you can convert it into the stochastic integral. So we can define exactly two martingales, right? So here's the martingale M, and now I take a matrix A, which is a 2 by 2 matrix, and I take the martingale transform. So I take the matrix A, apply it to the gradient of U, and this gives me a new martingale, okay? And I can write it down, and this martingale is subordinate to the martingale M, right? And now you see, there's no conjugate harmonic function here, right? Right? So we take the conditional expectation of this subordinate martingale, of the subordinate martingale, given the z tau is equal to n, right? And then we again apply the inequalities. Here's Berholder's inequality. Here is the orthogonal inequality, right? Up to this constant, up to the constant. Now, the p norms of the function f at the exit position become these weighted little LP norms with the probability of exiting right at the point n, right? Okay. I mean, this is just elementary probability, right? And so when we rewrite the inequalities that I just wrote, they become the following inequalities. Then, in fact, one can show, there's one is really not there, one can show that if you multiply by pi times y, these quantities also become 1. And this is, one has to understand the behavior of this function at infinity, but the behavior of this function at infinity turns out to be 1. And that's probably why I have the 1 there, but it's a typo. In any case, these quantities also go to 1. So these become operators that as y goes to infinity, you get these operators, and they are bounded in little LP, right, for any a, and they're bounded, of course, in little LP with a constant cotangent whenever a is orthogonal. One can compute the kernels of these operators, but they become very, very messy. And the technique to compute these kernels is using occupation time formulas for these processes, right? But you see, you convert these kernels. So now instead of just having the matrix A there and the Poisson kernel and with poles at these 2 points, you're dividing by H, and then you have this multiplication by H here, right? So the question is again, do these operators give information on discrete singular integrals or discrete Hilbert transform, discrete Riesz transforms, and others, right? So here is the matrix that gives you, in the classical case, the Riesz transform. So if you were doing the first construction and you got to the point where you were studying these TAs without the 2H process, the TAs will turn by conditioning, right? Will turn those Martingale transforms into Riesz transforms. So see, this matrix has zeros, lots of zeros, but -1 at the k plus 1 entry, and then 1 here, right, on the first column. And so this is an orthogonal matrix of norm less than or equal to 1, right? And if you look at the kernels in this particular case that you get, here they are. Here they are. See, integral over RD, 1 over hx comma y. The problem with this is that we do not have a formula as nice as we have in one dimension, right? Or in when d is equal to 1 for this function, right? So we had this very nice formula for the function. In fact, we take the 1 over it, and we have even a nicer formula. And so when d equals 1, right? Here's the formula for the h. And if you look at 1 over h, then if you fix y, right? Okay, you see we have the integration there in RD and 0 infinity. Well, move the 0 infinity out, And you can see that for fixed y, this is really just a linear combination of constant, right, times the cosine of 2 pi x, right? And then we were able, with Mateusz Kwasnicki, compute the kernel of this operator. And here is a terribly big disappointment. See, because the probability, these projections of these discrete operators do not come back to the discrete Hilbert transform. It's got this extra factor. Right? So all that work, and well, there we were. Okay. See, but you know, here's what's the day. So one can also compute it as a Fourier transform of some function, a periodic function. So the reason I have -1 to 1/2, -half to 1/2 here, that I have 2 pi here instead of the usual, just I and C, right? But so the interesting thing here is the following, is that one can compute the Fourier transform, the discrete Fourier transform, about 1 over pi n, right? And it is actually given by this quantity here, the signum of c times 1 minus 2 absolute value of c, right? So then you can write the Fourier transform of the discrete Hilbert transform in terms of the Fourier transform of the Hilbert transform, right? Of the Hilbert transform times this quantity here, right? This function. So this is the discrete Hilbert transform that we obtained from the probability. We call it the probabilistic discrete Hilbert transform. This is the probabilistic discrete Hilbert transform here. So times this function here. Now, it turns out that these will allow us to prove the following theorem that rescues the day, that the discrete Hilbert transform, even though, is not just the probabilistic Hilbert transform, it is the probabilistic Hilbert transform convolved with a probability kernel. Right? So we have an LP bound for this gadget, and therefore, and the LP bound is exactly the cotangent, right? Cotangent of pi over 2p star. And then we have the probability kernel here. So then this then gives us the result that the discrete Hilbert transform is less than or equal to the probabilistic, the p norm of the probabilistic Hilbert transform, even though they're not equal, right? They're not equal. So we get this extra factor, right? And this becomes then, and we know that this is actually has the right bound. So then putting it all together, we finally get the LP norm of the discrete Hilbert transform is exactly the same as the LP norm of the continuous Hilbert transform, and is also equal to the norm of these probabilistic projections, discrete projections that come from Dubé processes. Any questions on this? Well, I know I'm almost right out of time here. I wanted to say one word about this kernel. So, there is a theorem of Buckner that says that if you have a function which is positive definite in RD, then it's actually the Fourier transform of a probability measure. And that theorem extends in many different directions to groups and to discrete spaces and so on. And that's essentially what's going on here using this last expression. But in fact, Kwasnicki and I had actually approved of these just based on the fact that we found an explicit expression for these and a lot of computations. I was very lucky to have Mateusz as a co-author because he actually did a lot of computer experiment with lots of sequences and so on, and he was able to make essentially this conjecture that up to a kernel, the discrete Hilbert transform is exactly this probabilistic object. And now, where do things stand in terms of this project, in terms of the discrete Riesz transforms? You see, one more word here. What we have here is that the probabilistic Riesz transforms, a Hilbert transform, is the Hilbert transform plus an error term. And the error term is fairly well behaved. It's got the Hilbert transform in there because it's got 1 over pi n in front of it, but then it's got this factor, right? And you can, of course, see it here too. It's got the discrete Hilbert transform, and then it's got this factor. So one can prove a similar formula for in higher dimensions, but because we do not know how to compute this function h in higher dimensions, like nice as these, right? This function is really, really nice. So if you take this expression and just start doing Fourier transform with the representation that we have up here in 1 dimension, right? Bring this inside and then use Plancherel and all sorts of stuff. You know, after many pages of calculations, you know, patience and so on, you arrive at these formulas. But we don't have the kind of understanding of this function in higher dimensions, the periodic Hilbert transform. So let me stop here. I think it's 50 past the hour. I don't know what you typically do. I'm using our style of our seminar here.
Thank you very much, Rodrigo. I think that's a perfect amount of time. We usually like to have some time for questions. So thank you for an excellent talk. So are there any questions from the audience? I actually have some, well, I have a number of questions, but I probably shouldn't ask all of them, but maybe just a couple. So you said, I think early on that when you look at the boundedness of the Hilbert transform on the real line, it's equivalent to the boundedness of the periodic Hilbert transform, let's just say on the interval. And I think you said that it's sort of easy to see that those are equivalent. I was wondering if there's a probabilistic proof. So you showed sort of the how to do it probabilistically on the full real line using sort of this just the Brownian motion in the upper half plane. Is there a way to do it directly for the periodic one using Brownian motion, possibly Brownian motion on the disk or something?
Well, you know, you mean to do it for the discrete version?
No, I was thinking more for the periodic version, just on the
interval.
Oh,
the periodic version. Yeah. Oh, yeah. Sure. Yes. Exactly the same way. Yes.
Okay.
Yeah. You apply Ito's formula and then you rotate. You know, so this is going to this is always going to the rotation of the gradient of the u. So you take the function in the unit disk, right? You take the function on the boundary and then you take the extension of it. And that gives you a harmonic function. You apply the Ito formula, and then you rotate the gradient inside the stochastic integral, right? You see, and actually these martingales, they're mutually subordinate, right? And of course, so not only h of f is less than f, but f is cotangent, you know, the cotangent factor times f. But f is also less than cotangent of h of f. But you know, this is just the fact that h squared is equal to -1, right? Yeah. So yeah. So in the disk, it would work exactly the same way. Yeah.
I guess the other question I had, so I'm not so familiar with the discrete Hilbert transform, but so I mean, of course, I know with the Hilbert transform, if you know, as I think you mentioned at the beginning, you start with a harmonic function, you take the Hilbert transform, you now get the conjugate harmonic function. So there's this connection to to complex analysis. Is there a similar thing for the discrete Hilbert transform? I don't know what that would be, but is there some?
You know, so all that is actually fairly well explained in one of these articles that I gave. And there is no connection. There is no connection to discrete sort of a complex analysis. It's one of the problems, right? See, another problem here is the following. So one of the stumbling blocks, even with the probabilistic arguments that happened before, is that there is no orthogonality only occurs when the martingales are continuous, right? There's no orthogonality for discrete martingales. The process is, you know, you can check and then you see, all right, so there's no, they reduce to zero. The martingales. So people actually have tried to use the semi-group theory, right, in this sort of discrete semi-group theory. So you can get actually. So if you look at this paper, our Cozy, Domelevo, and Peter Mikkel, they actually have some sort of representation. Probabilistic representation for discrete Hilbert transforms, actually various types, but you cannot apply. You don't get constants. You get constants. Okay, you get LP constants, but those were around for a very long time. So somehow you really need the continuous martingales, right? And the advantage here is that you're working with continuous martingales, but the boundary, as they approach the boundary, right, as the condition process approaches the boundary, you just pick up, the integers. So,
okay, well, thank you.
That's a long answer, but yeah.
Yeah, no, that makes sense. Are there any other questions?
So in the continuous case, when you define this Hilbert transform, so as you mentioned, you can first take a function and take the harmonic extension, and then take the harmonic conjugate, and then you restrict it back. So this description is apparently conformal invariant. So,
exactly.
Yeah. So in this sense, in the continuous case, the problem on the upper half plane is essentially equivalent to the corresponding problem on any simply connected domain.
Absolutely.
Now, what if
simply connected? So in a simply connected domain, you can prove the boundaries of the conjugate function, but it will be with respect to harmonic measure.
Okay.
Right? So if in the disk, you start from zero, and so you exit with a uniform distribution. In the upper space, you start infinity, you exit with a uniform distribution. But if you were in, say, a simply connected region, then you will be with respect to the harmonic measure.
Yeah. But my question is more about the corresponding picture for the discrete Hilbert transform. Are there other types of for example, if you move to the unit disk instead of the upper half plane, there might be some other more natural type of discretization that might not be conformally equivalent to the discretization you take in the upper half plane. For example, on the unit disk, a simple discretization would just be maybe evenly divided the boundary into finitely many points, and that may not be conformally equivalent to what you are doing in the upper half plane case.
Mm-hmm. Yeah, I mean, that's an excellent question. I do not know. I mean, I have not explored it myself. Yeah.
Okay.
But what is the analog in the disk of these? I mean, following Calderón-Zygmund, I mean, I guess you will just take the kernel and discretize it in some way, right, on the boundary.
Right.
Yeah.
So you can do the similar type of conditioning on the partition points, but I'm not sure what kind of estimate would that be.
Yeah, why will they? Yeah, I mean, I think that there is. I think if you look, maybe I did these once, or maybe with one student. I think if you look at Stein's, Shakarian real analysis book, I think they may have the periodic Hilbert the periodic Poisson kernel in the unit disk, in the circle, and the torus. Yeah.
Okay.
Yeah, it's a good question. Yeah, I don't know.
So I think just to clarify something you just said, Rodrigo, when you let y go to infinity, basically you're letting the Brownian motion start at infinity, so it has a uniform distribution. Okay. Okay.
Yeah. Well, up to pi, you have to multiply by pi, whatever. Yeah. But you see, there's another. So I did not really do Gandhi-Varopoulos here, because so their idea was to start the Brownian motion, right, at a point x comma y in the upper half space, and then look at the probabilities, right? Integrate with respect to x, right? So you start the Brownian motion in the upper, in the hyperplane with the Lebesgue measure. So you integrate another Poisson kernel, and then that process x's the upper half space exactly with the Lebesgue measure, except there is no longer a probability space, but everything works, right? I mean, so they actually did that construction, and then they did this time reversal of Markov processes, and then let the y go to infinity, and what they got is this process that start at time minus infinity and ends at the at our end, right? On the real line in 2 dimensions, right? With the Lebesgue measure at time t equals 0. It's a very clever construction, but it's just sort of very technical complication that I don't think one really needs for these problems, because you can just start at a point and integrate it out and let the y go to infinity after properly multiplying.
Okay, any other questions? Okay, I guess let's thank the speaker again. Thank you very much, Rodrigo. That was
thank you. Thank you very much for the kindness and for the invitation to be with you.
It's our
I
pleasure.
hope we can do it in person sometime.
I hope so too.
Yeah.
I don't know if I think Costa, did you stop the recording?